far down the mass scale, talking about X-ray binary populations and their potential for being an important contribution to feedback really across cosmic time. And I just like to highlight, I have many kinds of collaborators on this type of science, but I want to give a special thanks in particular to Brett Lamer, whose work has helped contribute many slides to this summary talk today. So just to start off and orient us into what I mean when I say X-ray binaries, I'll be using this term kind of broadly, which can encompass low mass, high mass X-ray binaries, ultraluminous X-ray sources, but broadly, I mean binary star systems in which accretion happens onto a stellar mass compact object. So a black hole, stellar mass black hole, or a neutron star. And these are really key astrophysical probes of astrophysical phenomena like stellar evolution for massive stars, the processes that govern evolution in binary systems, obviously extragalactic compact object populations, so our stellar mass black hole demographics, neutron star demographics across different galaxy types. And they're also probes of the physics of accretion and mass transfer, and sometimes at the extreme. So as we heard just a little bit about with one of the questions, these sources can reach really extreme ultraluminous accretion states, so highly super Eddington accretion onto neutron stars. And so they really offer an interesting probe into the physics of accretion in those regimes. And then finally, I won't be focusing on this, but there's the potential for such systems to ultimately evolve into sources of gravitational waves. So if they can evolve into close, for example, black hole, or black hole neutron star systems that might merge in a Hubble time, they might be progenitors of gravitational wave sources. But why should we care about X-ray binary feedback in particular? So from the decadal, we already know that there are a couple of really big questions for the coming decade related to how reionization proceeded, which sources were actually responsible for reionization, and related to this, trying to understand what are the conditions that actually lead to the escape of ionizing photons in early galaxies. And so as the first stars form in early galaxies, so too should the first accreting stellar mass black holes. Obviously, these evolve from massive stars. And so X-ray binaries really, in addition to sort of operating in tandem with the stellar populations, they have some favorable characteristics that make their feedback important in the context of reionization and really across cosmic time. So namely, at high redshift, because X-ray binaries have hard spectra, they, might be these prolifics or producers of soft photons that, if they can escape their galaxies because of their longer mean free path, can actually directly heat the intergalactic medium. So this would actually be kind of like a pre-treating of the IGM prior to the epoch of reionization. In addition, they also may produce copious amounts of high energy ionizing photons. So again, because of their hard spectra, they may produce photons in copious amounts at energies that massive stars are maybe not able to produce. And in addition to that kind of ionizing feedback, they may produce mechanical feedback via jets or strong disk winds and outflows. And that kind of feedback may actually facilitate the escape of ionizing photons by sort of creating favorable conditions in the ISM carving channels, for example, that allow photons to escape from the early galaxies. So we need to have a few ingredients to understand this contribution to feedback. So here I'm actually just showing an image of Hera 11 with the Chandra 0.3 to 5 keV contours on an HST image, just as kind of an example of how X-ray feedback, toy model of how this might operate. So in order to understand our X-ray binary feedback, we need to know a little bit about the radiative and mechanical output from our population. And you can see here, these are sort of starburst 99 models for say a 10 to the 7 solar mass burst, how ULX mechanical power, if it scales with the radiative output of the source, may actually operate on timescales similar to feedback from stellar winds and supernovae, but also slightly more prolonged. But we also need to understand this output as a function of the physical properties of the environment. So of age, of metallicity, of the mass, as a function of burst mass, and so on. And so here, for this particular example, in HERA 11, this knot where we actually think some of the Lyman continuum emission might be leaking from has this age, which might be actually particularly favorable for strong feedback from ULX in the form of mechanical power from like a ULX wind. And we also need to know something about the intrinsic and the emergent SEDs for our X-ray binaries, whether that be ULXs, high or low mass X-ray binaries. So these are kind of the key ingredients to keep in mind, some of which I'll be touching on in this talk for understanding. So when we say X-ray feedback, we want to think about some of these key properties. And so the focus of this talk in particular will really be on the things that I, as an observer, think are sort of easiest at present for us to actually measure for X-ray binary populations. And that is the radiative output as a function of the host galaxy properties. So in particular, the host galaxy star formation rate, stellar mass, and metallicity. And that gives us what we call the X-ray scaling relations for X-ray binaries. So I'll then talk about the applications of these scaling relations for X-ray binary feedback as a function of cosmic time, and what the prospects are for AXIS to really contribute to this space. There's a lot of other things that I mentioned earlier in this slide with my sort of toy model that I really won't have time to talk about. And I leave up here a multitude of references for people that are interested, but namely, I won't really have time to get into this detailed idea of the coupling between the radiative and mechanical output for sources, really how this output scales in a detailed way as a function of stellar population age, as it's a difficult thing to measure at present. I don't have time to talk about our SED models really for these sources, but this is something that I'm interested in working on. So if people are curious and we have time at the end, I'll be happy to take some questions on that. So I'm going to break my talk today into 3 parts. Broadly, kind of to give a whole picture of how we might effectively measure X-ray feedback across cosmic time. So in the first part of this talk, I'll be focusing on basically our existing results using current X-ray facilities. And these are really limited to nearby galaxies where we're a lot of the times looking at resolved populations, but sometimes doing galaxy integrated studies. For the second part of the talk, I'll move more on to theory and talk about the evolution of the X-ray binary scaling relations with cosmic time and what the implications are for X-ray binary feedback at high redshift. And so as I say, this is mostly a theoretical work since we don't have the ability at present to peer back quite this far in X-rays, but we do have some ability to benchmark with current deep field results. And so I'll touch a little bit on that. And then finally, in the third part of the talk, I'll really talk about how AXIS can contribute to this field as a more direct probe of the evolution of X-ray binary scaling relations as a function of cosmic time. So for the first part, as I said, this will be focusing really on what I call today in my little shortened picture of cosmic history. And so the first thing to kind of orient us when we talk about X-ray binary scaling relations is that we've now known actually for decades that X-ray binary emission scales with host galaxy properties. So here I'm showing a deep Chandra image of M83. On the right, I'll kind of fade in some cartoons of X-ray luminosity function for X-ray binary populations that you can get when you have great spatial resolution, like with Chandra or AXIS, and you can actually find point sources within, say, the diffuse emission or within crowded regions. So the first component of our X-ray binary emission in star-forming galaxies like this are low-mass X-ray binaries. So these are systems where the donor star is, let's say, roughly 3 solar masses or less, and these populations tend to correlate with the stellar mass of their host galaxies because they have these low mass donors. So on the right, you see that's an example basically of our sort of current constraints on the low mass X-ray binary luminosity function as it scales with stellar mass. The other major component are high mass X-ray binaries. So these have donor stars that are massive stars, typically like greater than around 8 solar masses. And maybe not surprisingly, these tend to correlate with the star formation rate of the host galaxy. And you can see that their luminosity functions actually look quite different. So in particular, the high mass X-ray binary luminosity function we know now from resolved population studies with Chandra flattens as you get into this sort of ultra luminous source regime. So basically at sources greater than the Eddington limit for roughly a 10 solar mass black hole, the XLF is pretty flat. And this actually has important consequences for us as observers because the XLF looks so flat, say relative to the HMXB luminosity function. The effects of stochastic sampling become quite important. So you really need to have high star formation rate to really sample well this portion of the XLF and actually get something that looks like the cartoon picture that I've shown here. So just that's something to keep in mind as I go through this talk for us as observers. So high star formation rate means, individually a galaxy with a really high star formation rate or building up a large enough sample such that you get, statistically significant total star formation rate for sampling this luminosity function. So this is for our scaling relations for star formation rate and stellar mass. But as is usually the case, this isn't actually the full story. So if we begin to look at galaxy subsamples, for example, just focusing here on low metallicity galaxies as probed by their gas phase metallicities, they're actually not well fit by these relations that I've shown, where we only take into account star formation rate and stellar mass. And in fact, this is sort of most evident if you move into this ultraluminous X-ray source regime. So because of this, recent work by Brett Lamer looked at actually a sample of galaxies from the Chandra archives as a function of metallicity. So now the dotted blue line is the HMXB luminosity function from the previous slide, where it didn't take into account metallicity. And each panel shows instead the new metallicity-dependent model for the HMXB luminosity function. And so what this actually showed sort of for the first time is that this relationship between the high mass X-ray binary luminosity, star formation rate, and metallicity is driven primarily by a change in the bright end slope as a function of metallicity. That is sort of the number of your most luminous sources that you get as a function of metallicity. And this was seen in population integrated studies prior to this work, but this showed this sort of physical change in the luminosity function, which really corroborates some of our physical understanding for why something like this might happen, which is that at low metallicities, your stellar winds are weaker. So this is really actually a stellar evolution and a binary evolution effect. So when the stellar winds are weaker, your binaries are able to retain more angular momentum, which leads to tighter orbits. The primaries also retain more mass, so you might also get more massive compact objects. And this basically translates to more efficient formation of your very brightest sources at low metallicities. And so if you actually take those metallicity-dependent luminosity functions in the previous slide and integrate them, you can get something like the following, where the white line is now basically sort of collapsing all those panels as you've integrated them to show how the total radiative output from your HMXB population scales as a function of metallicity. So on the bottom axis here, I'm showing metallicity. On the top axis is a sort of rough redshift where the universe has sort of that mean metallicity. And so the galaxies that were used to derive the relations in the previous slide are the following. It's 55 relatively nearby galaxies, totaling about 5 megaseconds with Chandra. You can see that there starts to become very large errors at basically low metallicities. And this is because basically galaxies at these very low metallicities are really still rare in this volume where we can resolve populations. So, and they tend to be, if we find them, low mass galaxies and therefore pretty low star formation rates. So building up a statistically significant sample at present is tough, just with the archives or even with new Chandra observations. So this is a place, obviously, where AXIS really could provide a significant improvement through its high resolution capabilities and high sensitivity to get this statistically significant sample of what I'd call high redshift analogs. So the types of galaxies that are kind of rare nearby, and so that we need to probe out to larger and larger volumes. So with all of these local scaling relations in mind, I want to move on to part 2, which is more focused on the theoretical predictions for the evolution of these scaling relations as a function of cosmic time. So in order to understand how we get this theoretical evolution, we need to know a little bit about binary population synthesis, which in short is the process by which we model the evolution of a whole population of binaries. In this case, we're talking about X-ray binaries. So we initialize our population with prescriptions for, say, the binarity fraction, the separations, the initial mass ratio distributions. We evolve them as a function of key properties that we vary, like metallicity, common envelope efficiency, the strength of the stellar wind, and so on. And this gives us a grid as a function of those key properties like metallicity for the time evolution of our specific X-ray luminosity for any co-Ebel X-ray binary population. So here I'm showing from Fragos et al. In 2013, the case for solar metallicity. And this can be broken down then from our population synthesis into high mass and low mass X-ray binary components. And likewise, this can be looked at for different metallicities. So here again, we see that the case of what we saw observationally, where the low metallicity models produce significantly more X-ray luminosity per unit stellar mass. And these happily agree, at least relatively well qualitatively, with some results we have from the Chandra deep fields. This is the intermediate metallicity, like 0.6 solar roughly for HMXBs only, but at least it looks pretty good. So that's encouraging for us for using these kinds of models and evolving them with time. So we take the whole grid of these binary population synthesis models, and then we can couple them with results from cosmological simulations for the evolution of things like the star formation rate density, stellar mass density, and mean metallicity evolution of the universe. And in doing so, we actually then can produce the cosmic evolution of our X-ray binary scaling relations. So the top panel shows HMXBs and the bottom panel LMXBs for two sort of extreme models where we vary these parameters, like common envelope efficiency, for example. And I'm now going to fade in what I'll describe on the next slide as sort of a best performing model, but just to highlight why these relationships evolve as I've shown here. So for the HMXBs, this is again the case of a metallicity effect primarily, where we have weaker stellar winds, tighter binaries, and more massive compact objects. The evolution of our LMXB component as a function of redshift has more to do with the stellar population age. So on average, younger stellar population ages at higher redshift leads to more massive donor stars and possibly higher accretion rates. And so just a takeaway from this, from our cosmic evolution from the theoretical simulations, is that X-ray binary feedback is a strong function of redshift. And this is, can primarily be seen as due to the cosmic evolution of mean metallicity of the universe and the sort of average stellar population age as a function of time. So the best performing models that I showed on the previous slide are basically benchmarked with our current deep field constraints and low redshift results. So from the Chandra deep field south, 7 megaseconds, these results we have are basically based on stacking about hundreds of galaxies that are close to the center of the field where the PSF is still really sharp. So this is sort of our current best. We go up to about redshift of 3. And I think you can already see where I might be going with this in terms of how AXIS could do a lot better, particularly with a sharper PSF across the field of view than what we have from something like the Chandra deep field. But before I get into the prospects with AXIS, I want to talk about, why we want to push specifically beyond redshift 3. So why do we care even about the X-ray scaling relations beyond redshift 3? So if you take the theoretical relations for this evolution of the X-ray binary scaling relations, and you convolve them with the evolution for stellar mass per volume and star formation rate per volume, you can get an idea of the X-ray emissivity as a function of redshift or age of the universe. So this is for the best performing models, LMXBs and HMXBs. And here then is some constraints potentially for AGN. And so the important thing to note is that our current best deep field constraints are roughly redshift 3. And as this cartoon sort of shows, we may actually see that HMXBs in particular become the sort of dominant component of the X-ray emissivity at redshifts, let's say roughly greater than 5 or 6. So there is interest in probing beyond this redshift 3 as we start to see sort of what I call the rise of X-ray binary feedback or emissivity at higher redshifts. And you might say, okay, well, these are just theoretical models that you've extrapolated. We do have some indirect results already from HERA. These are 21 centimeter measurements. These are indirect probe of the X-ray binary, strength of X-ray binary component at redshifts greater than 6. And these are, I would say, consistent at least with these population synthesis models, perhaps even predicting higher X-ray luminosities than these population synthesis models at low metallicities. For the sake of time, I will skip this only to say that basically HERA will be capable of having this indirect probe on X-ray binary feedback at very early times, redshifts, greater than 10. And, depending on the strength of your X-ray binary component, you see a very different, thermal and ionization history for the universe. So this can affect what basically the strength of X-ray binary feedback can affect how reionization proceeds. So finally, to wrap up, I want to talk very quickly about some prospects for AXIS in this space in probing more directly X-ray binary feedback. So the key attributes of AXIS for actually directly contributing to this field are, not surprisingly, the high spatial resolution, but in particular that we'll have this really great sort of a resolution across the field of view. So in a field of view average sense, coupled with high effective area, that would allow us to actually dramatically increase the number of galaxies, star-forming galaxies that we can detect in a deep field. And that high spatial resolution will also be key actually for localization, because we don't want to just detect our star-forming galaxies in X-rays, but we want to understand the host galaxy properties relative to our X-ray detections. And so having this nice sharp PSF that be well matched to other multi-wavelength facilities allows us to not just, again, detect the star-forming galaxies in X-rays, but also understand the X-ray scaling relations for our star-forming galaxies in a deep field. And so if we take the scaling relations that I've already talked about throughout the talk, and we convolve them with the measured evolution of galaxy stellar mass and star formation rate per stellar mass of the galaxy main sequence, we can get predictions for X-ray number counts for star-forming galaxies out to redshift 8. So on the right, I'm just showing these predictions in a number of redshift bins. Again, just to illustrate, the key thing being here that while there are other surveys that we might have going forward that might cover large areas on the sky, they're not going to be able to push really beyond redshift 3. Whereas an AXIS deep field, not only this is a little rough in terms of an estimate, really would actually be able to probe into this redshift regime of interest where we might start to see the rise of X-ray binary feedback. And that's just sort of exemplified by this figure that I've continued to show on the right here. So what does this mean in practice? It means that AXIS could actually detect orders of magnitude more galaxies than we got from the Chandra deep fields. So the gold points are the 7 megasecond deep field constraints that we have, showing again how we can probe up to about redshift 3. That was, our stacking our galaxies near the center of the field. Again, hundreds of galaxies. In this redshift regime, AXIS can give us thousands of galaxies, even in multiple redshift bins, thousands of galaxies, which would give us dramatic improvements in this regime we've already studied, but additionally push beyond this. So it has the capability to get us even hundreds of galaxies, out from redshift 4 through 6 at least, and possibly pushing to redshift 8. This depends a little bit in terms of exact number counts on our deep field specifications and the galaxy properties really as a function of redshift. We've seen some new results from JWST that we have, highly star-forming galaxies, potentially very massive galaxies. That has some interesting implications for X-ray binary feedback at those epochs and what our predicted number counts are. But certainly it will be a dramatic improvement over what we have currently. And so I'll just leave up this as my sort of summary slide, that AXIS really has this unique capability to be a more direct probe of the evolution of X-ray binary scaling relations in a way that'll be complementary to indirect probes that we have at even earlier cosmic epochs from second generation interferometers like Hera or SKA. And I'll take any questions if we have 30 seconds or a minute. Thanks.
Yeah, sure. That was really interesting. That was really cool. I mean, I think you can really understand how you need this deep field and sensitivity across a wide area to get, the rise of XRBs. So yeah, my actual question is on the sort of the lower metallicity side. Is the reason you can't just, observe a lot of nearby dwarf galaxies because they're too faint and the star formation is too low, or?
So you can definitely observe them, and we have tried. The star formation rates are low, so the chance that you actually get any sources at the bright end of the luminosity function is, I guess, widely varies. And so I would say a good benchmark to think is that you can have a pretty well sampled luminosity function for a star formation rate, say greater than 3 solar masses per year, but it'd really be nice to have like 10 solar masses per year. And so some of these dwarf starburst galaxies, though they're starburst, their star formation rates are the order like 100 solar masses per year, right? So you can start to imagine how many of them you might need to actually build up a statistically significant sample in terms of total star formation rate. And especially at that extremely metal poor end. So when you go to like 10th solar or less, which is really the regime on that plot that I showed that's not well filled in, those types of galaxies, just in terms of metallicity alone, become quite rare. So you really need to push out to larger volumes like, not just 30 megaparsecs, 100, 200, and that rapidly becomes, I would say, difficult to do with the effective area we have for current facilities.
Great. So Daniel Wang actually has a question. How could the confusion with weak AGNs be overcome when high Z galaxies are observed?
Yeah, that's a great question. I think my very short answer would be that you just need multi-wavelength, supporting data to do your best to actually, well, so for me, I would call that a contaminant. I know often, we're trying to rule out X-ray binary contamination or star-forming galaxies from AGN studies. I'm thinking about it the other way around, but yeah, I'd say you need ideally spectroscopic data. There may be certain emission lines, so nebular lines like with JWST that could be helpful in determining if something is actually something I'm working on currently. If there are emission lines that are sort of uniquely sensitive to a X-ray binary photoionizing contribution rather than an AGN. So that would be the ideal. In the absence of that, at least color selections for your galaxies. But that's the other reason you need a really sharp PSF, right? Is to actually be able to match well with other multi-wavelength facilities like that. But it will be difficult. I will say that there will be probably a gray area where it's very difficult to, effectively say, is something a very low luminosity AGN versus a galaxy dominated by a strong ULX population.
Okay, great. Well, thank you so much for both of